Good morning to everyone. Myself, Shahul Hamid. In this video, we are going to continue our discussion about testing. In this video, we will discuss about the strategies of software testing. The contents of this video classes are taken from this book. I suggest you to read out the original sources for a better understanding. Let us start our discussion with defining what does software testing strategy actually refers to. The meaning of the term strategy is defined as follows. Strategy refers to an art of planning and directing an important activity. Okay, planning and directing an important activity. Testing, as discussed earlier, is a very important task which needs to be properly planned and strategized. Typically, many kinds of strategies can be used to test softwares. Different software testing strategies are simply the application of common sense to how to approach testing. Okay, broadly speaking, these testing strategies can be imagined as a spectrum, where at one extreme end, you wait until the entire software is built and then you start testing it. Okay, though this idea looks attractive, this will accumulate huge amount of errors and will be difficult to debug them. This approach is called as lazy testing. While on the other end of the spectrum, we can be extremely proactive and test the software on a daily basis. Even this approach is not optimal. So, as you can guess, the optimal testing strategy lies somewhere in between. Typically, unit testing is carried out on a day-to-day basis, almost on a day-to-day basis, whereas integration testing will be carried out less frequently and once the system is near completion. Once the system is near completion, it will be subjected to system and acceptance testing. Okay. Unit testing will be carried out on a day-to-day basis, whereas integration testing it will be carried out less frequently. And finally, when the system is near completion, it will be subjected to system and acceptance testing. This is the most common strategy followed in most of the IT industry. We will see the unit and integration testing in detail in this video. Now, let us see some general rules of thumbs or conditions which should hold true for a good software testing strategy. That is, good software testing strategy should have all these properties mentioned in this slide. First, the requirements, which is the core part of the software development, should be clearly and quantifiably specified. First, okay, quantifiable means one should be able to measure how much progress have been made in terms of completing a requirement. Next, the testing objectives should be clearly mentioned. That is, the objectives of testing should be clearly mentioned. That is, what aspect of the system is more important and in what sense the system is to be tested. This is the objective. Thirdly, users who are gonna test and use the software ultimately should be profiled properly. Okay, profiling and categorizing the users will help the testers to predict what the user might expect from the software and will make testing more relevant to practical usage, because it's ultimately people who are going to use the software. So if that is the case, these people, the customers or the client, should be profiled properly so that their expectation can be clearly documented and testing can be made such a way that their expectation is satisfied. Okay, next, rapid cycle testing. Okay, rapid cycle testing should be encouraged. This means that quick and short and efficient testing cycles should be encouraged. Okay, testing should be rapid. The next point is interesting. Okay, software should be designed in such a way that it should test itself for errors. This simply refers to error handling approaches. You might be familiar with try, catch, exception handling mechanisms in programming languages like Java and C#. Such exception handling mechanism should be properly used. The sixth point is also fairly straightforward, and it is discussed in the previous video on software inspection and reviews. The last point is quite insightful. Read it once slowly. Here the author encourages to review the testing strategy and the test cases themselves periodically. The statement implies that the processing of testing itself has to be tested. Now, let us see unit testing in this slide. Unit testing is the most fundamental and commonly used testing strategy. As discussed in chapter 1, in most of the software lifecycle model, we break down the software into small chunks or increments, and then we develop these small chunks or increments. That is, we break down the software into small parts and we develop each of these parts individually and then we put them together. Okay, the small increments can be practically as small as a function, a module, or a class, an individual function or a module, or else at the same time, these increments can be composed of several functions or modules. Okay, they can be either a single function or a collection of several functions or a single module or collection of modules. Okay, these increments. But irrespective of the way the increments are built, the idea is to build small, manageable software components one at a time. Okay, it's easier to build small, manageable software components. Okay, unit testing naturally helps to test these small increments we build then and there. After building a small component, this component can be subjected to rigorous unit testing. This unit testing will check the internal processing logic of the component within the boundaries of the component. Note that if several software components are developed parallelly, then each of them can also be unit tested parallelly. Okay, unit testing is generally independent. Each units can be parallelly tested. This is because we intend to check the working logic of the component within the boundaries of the component. Okay, a component as a single unit, we try to test it. Note that we interchangeably use the term software unit, function, module. The function, module, or unit, class, all of them here refers to the smallest unit of the software in this context. Okay, a function or a module can be a unit, a software unit. Okay, in this context. Now, typically the component or the module is tested to see if information flows properly into the module and comes out of the module in the expected manner. That is, the interface of the module or the function is tested. If data do not enter and exit the component properly, then the component is effectively useless. This ideology is similar to the black box testing ideology, which we discussed previously. Any testing strategy will have the flavor of both black box and white box testing. Okay, in unit testing, we also test whether the local data structures are working as expected. Then the test cases should be designed in such a way that all control paths are executed at least once. I hope this makes sense. For example, if you have a nested if-else statement in your module or in your code, then your test cases should be able to test all the cases of the if-else statement so that you are ensured that every individual case in the if-else statement works properly. Now, regarding the test cases, note that the design of the test cases for a unit, for a software unit, can be done either before coding the unit or after the unit has been coded. Okay, it simply means that the test cases can be designed either before you code the unit or after the unit has been coded. It depends. Then importantly, boundary conditions should be tested. During unit testing, the boundary condition should be tested. In your experience in coding, you would have noted that program often runs into error at boundary conditions. For example, array might perform weirdly at the 0th index, the beginning, or at the nth index. If you try to store an element or retrieve an element in the 0th index or nth index, error might happen. Okay, there is a higher chance comparatively. Likewise, error may occur if there are no element in the stack and you try to pop it up. Okay, you should be very careful. You should handle it explicitly such that when a stack is empty, you are not supposed to pop it. Similarly, error may occur when the maximum or minimum allowable value for a variable is encountered. For example, as I said earlier, if you try to store a very big integer in the int variable, it might lead to integer overflow and error might occur, register overflow might occur. Okay, such cases refer to the boundary condition. So the performance of local data structures at the boundary condition should be properly checked, and proper remedial action should be taken to handle them. As said in the earlier slides, it is necessary to have error handling routines within a software unit. That is, to have a software unit which can test itself robustly. In your C++ course or Java course, you would have learned about exception handling, that is the try, catch, throw logic. This is what is refers to as error handling routines. This approach is called as anti-bugging, where we try to crush the bugs then and there within a unit itself. One problem with exception handling is that people don't test the exception handling routine itself. The exception handling routine also should be tested. Okay, since the exception handling routine itself is a piece of code you are integrating with your original code, this additional code should also be tested. They should not introduce any new errors. I suggest you to read a book for the potential errors that could arise due to the exceptional handling routine. Adding this exceptional handling routine in your code might introduce some potential errors which are listed out in your books. Now, technically, let's see how the unit test procedure is carried out. Note that a component is not a standalone program in general. There will be dependency between the components, and for one component to function, you might need data or control instructions from some other component. This is quite logical. The components might be dependent on one over another. Okay, so it's not a standalone program. So it is essential to develop driver or stub program to unit test the software unit. What does it essentially mean is software unit is not a standalone program, so which means that you can't execute it as it is. So you need some additional piece of code like the driver or stub program to run a software unit so that you can test it. Okay, the driver program, let's see what is driver program and the stub program. The driver program is just a main program similar to the main code which you write in your C or C++. Okay, the driver program is just a main program which we write, and this main program passes the test cases as the input data to the software unit and then prints the result. Okay, this driver program is a meta program which simply passes the input test cases to the unit which is under the test and then prints the result written from the unit. Okay, that is the driver program which drives the unit test, hence the name driver program. Next, stubs. Okay, stubs are nothing but dummy code which serves as replacement for other modules invoked by the unit under test. Okay, as I said earlier, the unit is not a standalone, software unit is not a standalone program, it might be dependent on some other unit. Okay, so the stub is essentially a dummy program which gives an illusion that the unit under test is part of the whole software. Okay, the stub serves as a replacement for other modules invoked by the unit under test. Okay, the stub code simply returns the value or does minimal processing so that the unit under test can actually be tested. Okay, it serves as a replacement for the dependent units. Note that the driver and stubs are overhead here. These are additional piece of code which you are writing just for the sake of unit testing it. This is an extra effort and overhead. Okay, efforts are needed to be made to particularly write this driver and stub code. But it is necessary. So the idea is to keep them as simple as possible. You keep the driver and stubs as simple as possible. With this, we end up the discussion on unit testing. Okay, now let us start discussing about integration testing. Once you unit tested all the individual components, the next step is to incrementally integrate them and test them simultaneously. One logical question that might arise at this point is, if all the components are unit tested and are confirmed to work properly individually, then why do we doubt that they will malfunction when we put them together? Here I would like you to remind you two things. First, as I said in the earlier video, software testing is not theorem proving. Unit test in no way proves that the particular unit is error free. Rather, it tries to detect and remove as much errors as possible. So unit testing doesn't prove that the software component is error free. The second point is combining modules or units requires interfacing, which might introduce new errors. Okay. Interfacing means data flow between software components. Data flow between software components. That is the way the components are glued together to form the whole software. Okay, the way the softwares are glued together to form the whole software might reveal new errors which did not turn up during the individual unit testing. This interfacing, the way information is shared between the modules, might reveal new errors. Okay, that is the second point. According to your book, when integrating software units, data can be lost across an interface. One component can have an adverse effect on another. Likewise, subfunctions when combined may not produce the desired major function. Global data structures can cause problems. These are the typical errors faced during integration. So though you have unit tested the individual components, when we are integrating them, it is necessary to do integration testing. In essence, integration testing is a systematic technique in which you combine the unit tested software components to build the whole software, while simultaneously you conduct the test to detect errors due to this interface. Okay, two things are happening here. You are building the software as a whole. You are integrating the various individual components, and simultaneously you are conducting tests to detect errors which may occur due to interfacing between the components. There are two ways to combine the unit tested components. One way is to combine all the components, all of the unit components, and then test them as a one single complete software product. This, though looks simple, will lead to a big bang of errors, but it's not preferred. Since you are not incrementally testing it, you are merging all the components and then trying to test it as a whole. So this is not recommended. The second way is to incrementally combine one component after another in a systematic way and conducting integration testing parallelly. After every integration, you conduct a test so that the errors due to the interfacing between those two components can be tested then and there. There are two ways the software components can be integrated incrementally: top-down integration and bottom-up integration. Okay, the top-down integration is further divided into depth first and breadth first integration. These are essentially same as the DFS and BFS algorithm you have studied in your algorithm course. These type of integration are quite straightforward. I suggest you to read through the book to understand them. Now, let us conclude this video by discussing about regression testing, which is closely associated with integration testing. Okay, the term regression means that going back to an old state or simply to redo the same thing in our context. Okay, regression means that going back to old state or simply to redo the same thing. Okay, that is regression. As shown in this slide, as we integrate a new software component, there is a risk that the previously integrated modules which are already tested may malfunction due to the most recently integrated module. Okay, for example, let's say that two modules have been integrated already and have been tested properly, and then you are integrating a third module. Okay, and this new module can introduce new errors potentially. Okay, so this can happen. So we need to rerun some of the tests which we carried out earlier to ensure that the previously integrated modules are still working as expected. If you look at the graph on this page carefully, you can understand the functioning of the regression testing. In x-axis, we have the versions. For each version, we incrementally add or integrate a new module. From version 3, it can be seen that the older integrated modules are subjected to regression testing. Regression testing here simply means that a subset of test cases are re-executed to ensure that the addition of new modules does not introduce any new errors. How do you choose the test cases to re-execute? Okay, how do you choose a subset of test cases to re-execute is mentioned in this slide. If you look at the graph on this page carefully, you can understand the functioning of the regression testing. In x-axis, we have the versions. For each version, we incrementally add or integrate a new module. From version 3, it can be seen that the older integrated modules are subjected to regression testing. Regression testing here simply means that a subset of test cases are re-executed to ensure that the addition of new modules does not introduce any new errors. How do you choose the test cases to re-execute? Okay, how do you choose a subset of test cases to re-execute is mentioned in this slide. If you look at the graph on this page carefully, you can understand the functioning of the regression testing. In x-axis, we have the versions. For each version, we incrementally add or integrate a new module. From version 3, it can be seen that the older integrated modules are subjected to regression testing. Regression testing here simply means that a subset of test cases are re-executed to ensure that the addition of new modules does not introduce any new errors. How do you choose the test cases to re-execute? Okay, how do you choose a subset of test cases to re-execute is mentioned in this slide.